and welcome to Down to Earth with Terry Virts, where we talk about what matters down here on planet Earth. If you love the podcast, please subscribe and don't forget to give us a rating. Today, I'm excited to have Dr. James Head back with us. Dr. Head is a professor of planetary geosciences at Brown University, who has worked on projects ranging from training Apollo astronauts to be geologists, to robotic missions to Venus, Mars, and the outer planets. This is part 2 in a series about the planets. We were thinking we might do them all in one episode. We quickly got derailed as we only made it through Mercury and Venus. So this is going to be a multi-part episode. And Jim, thanks for coming back.
My pleasure. It's always a pleasure, Terry.
Where are you today?
So I'm out on Cape Cod. My wife and I, Ann and I, have a place out here on the Cape, about an hour and 15 minutes from Providence and Brown University. And it's a great place to be because we're away from more or less a lot of things and can communicate really well with the students by on Zoom and other kinds of things. So it's optimum for this kind of situation.
Are you still doing class, or is class? We're recording this in December, by the way. So is class over yet, or still finals?
The classes are winding down and finals are coming up here real soon. Yep.
I see Cape Cod beer in the background.
Yes, that's one of the pleasures of living out here. There's a lot of local establishments upon which this is one of the best to me. It's a locally run thing. They don't ship beer internationally, like off the Cape. Okay, and their motto, which I love, is Cape Cod beer, a vacation in every pint. So they're always. Ann and I were over there last night. Actually, we were. They just try all kinds of new things, and they're really innovative and creative, and it's just great fun. They're real explorers of the brew world.
Well, when this podcast is done, take it into them, and maybe they'll give you a free 6-pack or something for promotion.
Right,
I missed that.
I'm trying to get him to do a special beer on for the Apollo 50th anniversary. So we'll see how that goes. I'm working on it.
Yeah, use the podcast. I miss teaching. I do guest lecturing there at Harvard, and it's been since COVID. And I think in the spring, I have to do one more remote session. After that, I get back in person. So I can't wait to get back there.
Yeah.
When I am, we'll have to meet up and go check out the Cape Cod beer place.
Absolutely.
But yeah, well, let's pick up where we left off. So we were traveling outbound from the sun. I learned a lot about Mercury and Venus that I never knew. You think of them as these hot, dead worlds, but there's a lot of really interesting things happening there. So as we go out, I'm thinking Moon and Mars today. So which one should we start with? The Moon, since that's, right nearby?
Yeah, I think that's a good one to start with. Yeah, absolutely.
And you were training Apollo astronauts 50 years ago. Were you in kindergarten then, or were you a grad student, or what was
yeah, no, thing? It was my postdoc. It was I actually didn't get my degree until I started in 1967, I guess. I was still in grad school.
So did I.
Yeah.
I started then too.
Yeah. So I started my job at NASA then, at NASA headquarters, and I was it was one of those opportunities. I answered this ad. I was looking, I think I mentioned this last time, but I answered this ad in a college placement annual about jobs, and it had geologist 15 to 27, and then this number outlier 36, something like that. And so I turned to that, and there's a picture of the full moon, and it said, our job is to think our way to the moon and back. And I went, how do you do that? How could you not want to be part of that? It was the Apollo program. And so I called the number, got the job. There's a few little bumps in the road between, but it wasn't tough because they were looking for geologists, and it was a tremendous first job. But I had to finish my thesis at night for the next 2 years, and that resulted in this is why I have such horrible work habits and publish so many damn papers, research papers, because I'm still on that kind of like momentum from those days. But it was great. It was absolutely a fantastic experience. The astronauts, as you well know, being one, are all extremely bright and highly motivated people, and they're mission oriented. So if the mission is to go to the moon, and you got to learn some geology to accomplish the goal, they're in it, and they were just fantastic. I mean, fantastic.
That's exciting. One of my astronaut classmates had not quite finished her PhD when we got hired to be astronauts, and so she was working on the weekends to get that thesis done. And that's something I cannot imagine how much work that is. But that was what a cool time to be at NASA in the 60s. I feel like I was born a couple decades too late. That would have been amazing.
Yeah,
And so your job was to train astronauts.
yeah. Basically, so think about that picture, and it said our job is to think our way to the moon and back. My real job, my card said systems engineer, and I never had a course in engineering, and I didn't even know what a systems engineer was, but I was one. And what was that?
Right.
It was thinking your way to the moon and back. It's very, very simple, and it's an integrated picture. I worked for the Apollo program director, and traveled all over the place. Worked in astronaut training and site selection, mission operations. So we would essentially prepare the astronauts in training, and then work on this, major questions. Where do we want to go? That's
Right.
landing selection.
Right.
Well, what do we want to do when we get there? You don't just land and say, okay, we're here.
Right.
No. There's jobs to do. There's science to do.
Right.
There's exploration to do. So that was part of the job too. Traverse planning, site selection, traverse planning. And then once you buttoned up the crew at the Cape, and watched the launch, you shot over to JSC and mission control and worked in mission control while the astronauts were on the moon. And then we debrief when they got back. That was one of the most fun things, was debriefing when they got back, because we'd sit in the bottom of building 31, mission control, and building 30, I guess. Let's see. Yeah, 30.
30. Yeah, 30.
Yeah, sorry. 50 years. What the hell? Slip a digit. Give me a break. But we'd all sit in the basement in the dark and watch the movies and debrief, on the traverse and things like that. And it was absolutely hysterical to listen to them see themselves on the moon for the first time. It was priceless, and we had just a blast doing that. And so then we'd factor that back into the next mission. And then at the same time, we're looking at the samples and then talking to this other scientists and saying, what have we learned? What do we need to learn? And then we factor that into the next site selection and next mission operations, next planning, et cetera, et cetera.
And that was all from Neil and Buzz to Gene Cernan and Jack Schmidt. The final mission was 2.5 years.
Yes.
Less than.
Couple of years. Yeah, for sure. It's amazing.
That time, it's amazing how much you guys got done in such a short amount of time. When I think about the current program with SL, you and I have had many discussions about that. But the rocket was born in 2005, and it won't fly until next year, maybe, and that's only as half a rocket. So that's almost 20 years just to design one rocket, and you guys flew all those missions in 2.5 years is really amazing.
I think one thing about this is too, that really the story that I like to tell, that to me is the epitome of Apollo, was the science and engineering synergism. We work shoulder to shoulder with the engineers at every step of the way,
right?
And the astronauts and the operations people. Okay. And it was like, we were a team, unbelievable. I mean, it took a while to learn each other's language and learn how to, but the engineers, once they don't want to send sandbags to the moon, for crying out loud. Oh, what do you need? What a car? Let's see. What about that pallet on the side? We could probably
describe the difference. A lot of people, they think science and engineering is the same thing. And that's probably like, makes a PhD scientist's head explode. What's the difference between scientists and engineers? There's probably a lot of funny, anecdotes about that.
It's really simple. Science is simply this. I can make it really complicated, as everybody tends to do. It's very simple. It's just exploration of the unknown. Okay. Engineering is how you do it. It's how you implement all the goals and desires we have so that we can accomplish our scientific dreams, how to understand essentially the unknown. Maybe it's designing a submersible that you can go to the bottom of the seafloor. Maybe it's surviving in Antarctica for a month or two out in the field. Maybe it's going into space, for crying out loud. There's an idea. Yeah. Let's go into space. Maybe we could learn something there.
Sounds good to me. Well,
yeah, very simple. Very simple. Science is exploration of the unknown. Engineering is creatively getting you there. Okay.
I remember my classes in college, the scientists want to solve the equation perfectly and really understand the why and what's happening, and the engineers kind of don't care. They just need an answer that works. They don't need to solve the equation. They just need to get a number that actually works. And so it was an interesting difference. I like both, but so
I think I would just add to that too, the empirical approach, which is like, okay, if we can approximate this, is it good enough to
right,
take the next step? And you're right that the scientists might tend to say, no, we really got to get this down to the third digit,
right,
but we might not need that, to solve the implementation problem. Okay, so yeah,
right.
it's an interesting, and the language is
It is.
totally different, of course. I
Right.
mean, it's like it's not. This is if you want to be successful in science and engineering synergism, you've got to learn language. Okay, the other's
Mhm.
language, and that's
Right.
why shoulder to shoulder is so important. Because if you're not doing it shoulder to shoulder, you're going to waste a lot of time.
How much
Nobody
time?
a truckload.
So, so astronauts back then were all, and nowadays are half. We call them knuckle dragging fighter pilots. So, and I had the honor and privilege of doing my field geology training, which I think you were doing with Bill Mulberger, who was,
Yep.
the icon of Apollo training and stuff. And he was still, well, he passed away recently, but I got to train with him. He was amazing, so much fun. He hated vegetables. All he cared about was rocks. He called them anything that was growing like a tree or plant. He called them vegetables, and he was always grousing about, those vegetables are covering up the rocks. He just wanted to see the rocks. So talk just a minute, because we got to talk about the moon and Mars. What do you need to teach somebody about geology? Do they just go out and plug in a box and leave it there, or do they actually have to know and understand something?
Well, it's observational science. I mean, basically, geologists are like crime scene investigators, CSI. The
Mhm.
crime has already been done. It's a rock. Okay. Well,
Right,
that's nice, but how did that get there? You know what I mean? And so we
right,
have to take this crime that's already been committed, such as it were, and then
right,
involve it and figure out when it happened and how it happened and what went into it to make it happen. And that's
right.
that's basically it. So serious observational skills are required, and you need to be approaching it from a kind of an open loop kind of thing, in the sense that we don't know. Oh boy.
Were there any anecdotes where these knuckle dragging fighter pilots were bouncing around on the moon, and the human brain actually noticed something, and they were actually able to get science done
Oh,
because you would train them?
oh,
Yeah.
absolutely. And not just because we were training, because they're all bright, highly motivated people. I mean, like,
Right.
as any pilot knows, that situational awareness is is
Yeah.
just the point of the realm, man.
Right.
The point of the realm. And
It
so
is.
you if you didn't have situational awareness on the moon, then you were missing a lot. And all the pilots had situational awareness. So that's something I have to
Right.
teach my students. Okay,
Right.
who are training in geology. So we had a start on that for sure. They also were very mission oriented. It's like they knew they were on a mission, and they wanted to learn the goals and objectives, and then figure out how you implement those. So I think to me, the epitome was on Apollo 15, 16, and 17. These were J missions. Each had a rover on it, and they were
Mhm.
all scientific Lewis and Clark like expeditions to the moon.
Mhm.
I mean, amazing. 3
Mhm.
EVAs,
Right.
hundreds of kilograms of rocks, and so on. So basically, Dave Scott, the Apollo 15 commander, I would say would be, the epitome of in the first missions there, the J missions, like, okay, what it's like to do a complex scientific expedition. Dave said when he got back, one of the neat things about working with these people is, like, a couple of days after they would get back, they'd say, "Come on over to the house, we're bring the family, we're having a, let's have dinner, and so he'd sit there. It's like my kids are going, "Wow, did he? Who meant? He just came back from the moon." It was just great fun. But Dave said, he said, Jim, it was so much fun doing the geology that I didn't even know I had my spacesuit on. Now,
Wow.
I'd
That's
be
saying
looking over
something.
my shoulder to make sure that blue orb up there was kind of envisioned.
That
And
is saying something.
yeah, and he said I was totally in the zone, and totally in the zone. And there were so many times when that was epitomized, because when Dave, we knew we were landing in these huge mountains at the edge of this huge 1,200-kilometer diameter impact basin that formed 4 billion years ago. And so this uplifts rocks from deep, and we wanted to get the deepest rocks. And Dave knew, having studied these rocks, that the larger the crystals, the deeper they were, because they cool slowly with depth. And so he's walking across the surface of Hadley Plain, and he goes from meters away, Houston, I think we found what we came for. What did he see? He saw white rock with twinning, which is a way that cooling crystals form structure that reflects. He saw it, he saw the size, he saw it glinting at him in the face, recognized the size, and he said, Houston, I think we found what we came for. Sure enough, that was a really coarse-grained anorthosite, and it's called the Genesis rock because it's like, wow, that's what it is. So there you go, there you go. That's like, oh no, just get a shovelful. No, we're exploring here. And then on the way back from EVA two, I think it was, basically they were going back to the lunar module, and it's the end of the EVA, so we're oxygen supplies are down, they're not in critical danger, etc. But Houston is pushing them along.
Time to come in. Yeah.
The subtle.
I do. I do.
Like, but move it along here. We got another. And Dave and Jim, they're driving along, and Dave sees this rock full of holes. Okay, and what does that mean? It means there's gas that's come out of it in shallow lunar crust. That means it's very gas rich. And he knew from all the discussions we'd had and in the field that understanding what gas was in the inside of the moon, if any, was really important. So he looks at this thing and he said, I have to have that rock, not verbally, he just said that to himself. And so he stops the rover. He's the driver, of course, commander, and says, Houston, I'm having trouble with my seatbelt. I'm going to have to stop and fix it. Oh yeah, can't be falling off the rover. And so he gets off, takes the pictures, samples the rocks, brings it back, gets back on the rover, cinches his belt up and said, okay, we're good to go. And that's now in science, in lunar science, known as the seatbelt basalt, because it was really, really important. So those are the kind of things that, verbally or not verbally, those are the kind of things that the well-trained crews, and even, Neil and Buzz, all of them were really very, very sharp. So I have no problems with any of them. They were, in terms of the motivation, excitement, and devotion to duty and understanding the mission, et cetera, and making it happen. It's incredible.
That is awesome. So the mission of Apollo was what? To find out, scientifically, was to find out like how old the moon was, or how the moon formed, or how the solar system formed. What do we learn from the moon?
Yeah, it's the basic thing. The basics, broad scale goals were to understand the origin and evolution of the moon, and also be able to, we didn't know whether it formed hot or cold. We didn't know the age of it. We didn't know the age of the flat-lying dark Mare plains. We didn't know their origin. Some people thought they were dust. Some people thought they were lava flows. And we didn't know, we basically didn't know anything, okay? Actually, here's another one. We didn't even know what the far side of the moon looked like. Huh, wow, that's right. So,
did people get, so the far side of the moon, describe that. There's a big difference between what we see from Earth and what you see from the far side. Why is that difference?
Yeah, so the difference, if you were in orbit around the moon, you would see that, the near side, that is the side that continually faces the Earth, because the Earth is in synchronous rotation. It rotates once every orbit around the moon. Has a lot of flat, dark mare on it. Okay, these are less cratered than the surrounding terrain. So what's that all about? Some of them are big and circular. They look like giant impacts. The Soviet mission, Luna 3, when it flew by the moon and then viewed the far side back, there weren't any large mare. There was one mare area there, which they named Mare Moscoviense, and mostly just little piddling patches, and mostly just heavily cratered, bright terrain. So it's like an asymmetry between the near side and the far side, and that's really mystified people for decades. And now we know that the crust of the moon, this anorthositic crust, this is a certain kind of rock that often occurs in, it's a light rock. It's a less dense rock than more iron-rich minerals, and it floats to the surface when this intense bombardment occurs. And we know that is maybe twice as thick on the far side than on the near side, and that is what tends to account for the differences. And why that's different is a big debate. Some people think there's a huge impact that it hit on the near side and basically thinned it by excavating it and dumping it all on the far side. Other people think that the internal convection may have, moved some material from the near side to the far side. The Grail mission that we did, 2 lunar orbiting spacecraft that tracked each other and looked at the differences in rate of velocity, really showed the details of the thickness differences, et cetera, but it did not reveal the exact cause. So it's still
because that will measure the amount of gravity, and
Yeah.
that changes the orbit of a spaceship. And if you know how much gravity is there, you know a little bit about what's inside the moon. Is that how that works?
Right. It's the density structure, if you will, but
Right.
not the origin. So these things were
Right.
noticed early on because during Lunar Orbiter, we were of course tracking the orbiter spacecraft, the Lunar Orbiter 1 through 5, very, very closely because we wanted
Right.
to know to get the best possible orbit so that when Apollo flew, we would have the least opportunity for any mismatches in orbital configurations and parameters. And what was noticed by a couple of geophysicists from JPL, Muller and Sjogren, was that when the spacecraft went over the Maria, it changed velocity, and then when it got on the other side, it changed velocity again. And the idea was that, oh my gosh, there's a big density structure. Some people
Right.
thought, oh, it's just a lava, but no, it turned out to be uplifted mantle material density.
Yeah. Wow.
Yeah, and
They call
this,
that MassCon, is that right?
yeah, basically for mass concentration, and
Right.
this is probably what doomed the Luna 15 mission, because there was an early Luna mission which was going to land on the moon before Apollo got there, for example, and that was a really interesting story in itself. But this was a sample return mission, and if it had been successful, the Soviet Union would have gotten robotic samples back from the moon, rocks from the moon, prior to the time that Neil Armstrong and
Right.
Buzz got back. I mean, it would have been a huge propaganda coup, and they would have said,
Right.
oh, Americans are spending all this money. We just did it with a robotic thing. But
Right.
what happened is that the spacecraft landed long because they didn't, and hit a mountain because they didn't have the details of the mass cons. Okay, so yeah, so
that changes, so that different density on the inside of the moon changes the gravity so much that it changes the orbits of things flying around so much that it caused the Soviet spaceship to crash.
that's my understanding
That's
of
the
it.
thought. Yeah.
And
They
I
didn't
think
get English and SI units backwards.
no, that was left for us to do.
We'll get that. We'll talk about that when we get to Mars.
No, it's no, they're brilliant people, absolutely, but they
Oh
just
yeah, God, yeah.
didn't have the data. They didn't have as many orbiting spacecraft as we did.
Right.
Yeah.
So I want to talk about how mares are formed versus the craters. But my understanding, really, the reason there's lots of amazing things about Earth. The magnetic field, for one, allows life to happen, but the moon, in some ways, allows life to happen. I'm a baseball guy, and isn't the moon kind of like a catcher's mitt, where a lot of meteors hit the moon that would otherwise hit Earth?
Um,
It
yeah,
absorbs some of the
small,
impacts that we would get.
there's a small focusing effect. So if things are heading, going by the Earth and then by the moon, when they go by the Earth, it changes their orbit slightly. Obviously, that's it's like the little slingshot orbit insertion, things like that, where you can get into orbit by doing more and more flybys, and it helps change the orbit. And that's how we get out to, you ask yourself, gee, we're going to fly to Jupiter. Well, why are we heading towards the sun, for Christ's sake? You know what I mean? The answer is because we
fly by Venus on the way to Jupiter. Yeah.
Stop by Venus on the way to Jupiter, not because we really want to see it. I mean, we do, of course, but it's like to get a slingshot out there. So yeah, that's a factor there. But it doesn't really explain. People thought originally that all these dark holes on the near side was due to the focusing effect. And that just doesn't appear to be the case. The darkness in there is due to volcanic lava flows filling them up.
Right.
With their presence, the statistics aren't so different, actually, of big circular basins, okay? And they don't seem to be accounted for by that. The focusing effect is relatively minor because you don't have a lot of distance there, actually. You know what I mean? It's only a couple 100,000 kilometers. And so, you got to really say, okay, now we want to do, northeast 40 to get, hit the moon. And it's also not a very big object, you know what I mean? So.
Right. So the moon, the near side of the moon, it's not the dark side, by the way, it's the near side and far side.
That's right. It's a really important thing to, it's
Pink Floyd kind of ruined that for a lot of people.
Well, I'm a big Pink Floyd fan, so I blame nothing on them except a great decade. You know what I mean?
Well, we'll give them a pass.
Yeah, no, it is. It's I think something, I love to tell a story Dave Scott told me when he got back, which is that, I said, Chad, tell me what it was like. Oh, Jim, it's fantastic being in lunar orbit. He said, when you go into lunar orbit, okay, first of all, you go behind the moon, and you look back and you can see the sun and the earth, and then you go behind the moon, and he said, it's lights out. I said, wait a minute. So, okay. So yeah, he said, the only way you're in orbit around the moon is because there's a dark area with no stars. And it's kind of like, okay, let's go back to, to astronautics 101. I think I have to be in orbit here because, you know what I mean? It's like, it's all in phase.
That's amazing.
It's just a black hole. And then you can't see the sun, you can't see the earth. Then you come out of that, and that is the dark side, because in fact, there's no sun, there's no earth, and that's all she wrote. Okay, then that's why people want to have
city lights either.
No
city lights.
Not yet. That's why people want to have telescopes on the far side, because it's outside of radio interference too, and lots of other things. So you can do good astronomy from there. And then Dave describes, okay, you're coming around to the terminator, which is the line between sunlight and darkness, and of course, I think all the astronauts in that position on Apollo have described kind of lining up for the first view of sunrise on the moon. And of course, if you're not careful, it's like a bolt of lightning. It's you don't touch any switches. Oh, I can't. Like it. Right. And then once your eyes get adapted to that, then it's just beautiful. And then you slowly see, as you're going around towards the other terminator, that the shadows are getting longer. And then you go into a point where, the shadows are so long, then they just disappear, because but your eyes quickly adapt and you realize you can see things on the surface. And what is that about? That's sunlight reflected off the earth onto the moon. So you can see this at night when you look up at the moon. Look at the part that's not illuminated, but if you look closely, oftentimes you can actually see it details. And we actually put film.
See the dark side, right?
No, not the dark side. So the moon is rotating. So sun is, so it's actually, what you're seeing is the unilluminated part of the near side. Okay. So the dark side is always moving. It's the near side and the far side. The dark side is always moving. But what Dave pointed out was that you can see a lot. It's like being out. You've experienced this flying in a moonlit night, full moon night. You can see a lot on the ground. And we actually put high-speed film on board the Apollo missions later on, but I think about Apollo 13 on, to take pictures in Earthlight. And we got some of them. They're fantastic. They're eerie, but you can see features.
The moon at night. Yeah. I've never seen those. I'd love to see it. So my favorite picture I took, one of my favorite of Earth, is a time lapse of the Northern Lights, but you can see the ground really, really well because of the moon illuminating the Earth. It's nighttime on Earth, but you can see snow and blue ocean, and it's from the light coming off the moon down here. Yeah. It's the same thing, I guess, up there.
Absolutely. Yeah. So Earthlight's pretty amazing.
So the near side has these big mares that are volcanic. They're igneous, right? They're lava flows. And the far side is breccia. It's just millions of craters everywhere, and it's really white and bright. And why is the near side not as pockmarked as the far side?
Well, because a lot of it has been resurfaced or flooded by the volcanism. So a key thing here is you've got these big craters, okay, thin crust in a very general sense makes it easier for the lava to get out from the interior. So if you have thin crust, that means less material has to go through, and so it preferentially flows out on the thin crust, and that's on the near side. So you have big holes in the ground on the near side and the far side, but the near side has much thinner crust, and it's easier for the lava to get out. So that's, in a very simple way, why the lunar mare are dark. When you look up at the moon, I've never been able to see the man in the moon or the rabbit in the moon or the but it's up there somewhere, and you can see the differences there. And
okay. And the far side is deep dish. It's not thin crust, and it's because of that. There's not a lot of volcanism, and really, this is another interesting thing about planetary geology, I think, and you can correct me. I think crater count is really a measure of age, right? There's a way that you can tell how old something is by how many craters. Can you explain that?
And that's the inverse of your question. Your question was,
right,
why are there so few craters? Because the surface is younger.
Because it's younger, exactly.
Covered up older craters and then accumulates craters from that point on, which is the crater counting method. So if you form a new lava flow on the moon, it has no craters, okay? And then, we're talking geological time here, so we're talking hundreds of millions to billions of years. And plenty of stuff flying around, folks. And so that then it starts accumulating craters, and that's indeed one of the best ways we have. It's all rooted, though, in the Apollo sample return, because if we didn't have the actual rocks,
truth data,
those lava flows, and bring them back to the lab on the Earth, and then date them in the lab, then we wouldn't know the absolute age. Okay, so we wouldn't be able to put in. We can always tell the relative age: more craters, less craters. But is that 1 billion or is that 100 million? We don't know until you calibrate it. So that's what Apollo did too. It calibrated the lunar scheme, and furthermore, that's the basis for our planetary scheme. Okay, even though planets differ in their geological activity as a function of time, that radiometric age and calibrating the number of craters as a function of time, adjusted a little bit here and there, is really, Apollo contributed to the fundamental chronology of the solar system, period.
So two quick questions. Can you describe how you do that, how you date rocks, and can you describe bombardment and what that means for understanding crater counts?
Right. So you bring back a rock into the lab, and when a rock initially forms and solidifies, okay, like a lava flow on Iceland or Hawaii, okay, the elements in it, quite a variety of different elements, and some of them are radioactive elements, and they start to decay. And so you can then, at a predictable rate, it's kind of like an atomic rate, it's like not something we can say, let's change that. No, it's the way it works. Okay,
it's the same everywhere in the universe.
But pretty much as we know,
probably
would surprise me.
Right.
It's not going to change in Europe or Mercury. Okay, but so anyway, so the bottom line is we measure the decay, the amount that's still there versus the amount was there. And with that rate, you can calibrate it. I mean, Jerry Wasserberg, a professor at Caltech, was really one of the fundamental people. A lot of other people too. Ed Anders at Chicago and many European scientists were instrumental in dating those first rocks and really setting the chronology up. So then the second question is about
bombardment.
Yeah. So, in general, at the beginning of the solar system, this stellar nebula, by which I mean like this star that's forming with all this material floating around it in a swirl, okay, comes together to form the planets. And like I always say, Terry, to my students, if somebody's moving their hands too much, it means they don't know what they're talking about. So, there's a few little details to work. Yeah, hand waving. A few little details to work out in there somewhere. But no, we pretty much kind of know how that works. And so once all that stuff is largely swept up to form the planets, then the interplanetary space between the sun and between the planets, et cetera, is fairly devoid of debris, certainly compared to what it was like in that early chaotic period. And so, but there's still a lot floating around. There's material in the asteroid belt. Jupiter's interacting with the asteroid belt and pumping stuff out every once in a while. There are comets coming in from the Oort cloud way out there. And so there's always something going on, and you ignore them at your own peril. The dinosaurs ignored them. You can go ask them. Oh, no, you can't ask them anymore. Yeah, that's right. Yeah. Anyway, so that's the bombardment history. It's the projectiles that are still left around, and because you're not adding a huge amount to the solar system as a whole in the broadest sense, then there are fewer as a function of time. So that's
Right.
why we're fortunate that we don't have any of those big basins in the relatively recent history, and probably, certainly won't in our lifetime. Well, I wouldn't say that. It probably won't in our lifetime. But there's a decay in the population, a decrease in a number of these
Right.
spectrals. So the bombardment is generally decreasing. So we see that in the rock record between Apollo 14, between Apollo 15, 16, 17, and we see decay, a change in the difference in number of projectiles as a function of time, because we can date them. So that's what that's saying, is that it's quantitative testimony to the decrease in the number of projectiles with time, and we actually can not only understand that, but we can use that to date other surfaces in the solar system.
Right. So when you look at a place on a planet and there's lots of craters, you would think that was formed early in the solar system when there was a lot of meteors zooming around. And if a place is smooth and flat with no craters, you think that's a lot younger because it hasn't been hit by. And to also describe the number of millions or billions of years since the beginning of the solar system, since the moon was formed, and so on.
Yeah. So it's yes, that's true. That's it. That's exactly what you would infer from that. And you saw a heavily cratered surface, that would be old.
Right.
And again, heavily cratered, yeah, and lightly cratered, that would be young. There's variations on that theme. Sometimes materials can be so porous that they lose craters. You know what I mean? Shaking with an impact or something. So you have to be careful about that. But in principle, that's our guideline. Absolutely. And then the question:
how old is everything?
Yeah. So,
well, the universe is what, 13.5 billion, something like that.
Something like that. Yeah.
Yeah.
This and then of course the origin of the solar system is about roughly 4.5 billion years ago.
Well, can we talk about that real quick? So that's really 4.5 billion Earth years at our inertial reference frame. If you were on some other part of the universe that was going 0.99 the speed of light with respect to us, that would the watch would move slower there than here. And so do you need to be precise about that, like what inertial reference frame you're talking about?
Only if you're traveling outside the solar system, and I tend to stay.
Right. You're a solar system guy.
Well, I'm a neighborhood guy. You know what I'm saying?
Yeah.
But
okay, so 4.5 billion versus 13. So our solar system was formed 9 billion, 8 or 9 billion years after the solar system. So was there another galaxy and star and that exploded and that's what made our solar system?
I don't know. I mean, the bottom line is that I think the cosmos is so vast that you kind of lose frame of reference. We talk about constellations, we talk about solar systems, we talk about galaxies. It's literally an incredible onion, if you will. It's like a matryoshka. You know what I mean? You oh yeah, here it is. You open one up. No, there's a little one inside here, and you open another. There's another one. There's another one, and that's both space and time. I mean, it's incredible, and you need to talk to an astronomer about how to fit all that together. But yeah, I'm humble enough to just be dealing with 4.5 billion years of history and trying to figure that out. And we're excited now because for years since the Apollo program, we've been trying to figure out what the history of this solar system is all about. Okay?
Right.
And now, I think I mentioned to you before that a friend of mine, Stephen Kane, an astronomer at UC Davis, came to me and said, "Jim, I need help." He studies exoplanets. He said, "I need help. I have 50 Venuses. What do I do with them?" I go, "Oh, I'm hyper. Yeah, this is incredible." So we say, "Oh, wait a minute. We have comparative planetology for Venus." Right. And we're working very seriously on comparative solar systems. So that's part of the answer to your question is, well, wait a minute, where is that one? How old is that? And what's it look like? And so on and so on.
Right.
And that's the new field that excites me so immensely, which is comparative solar systems. And we had a conference in Houston a year ago or so, in which the title of it, we organized it was Exoplanets in Our Backyard, okay, which is like, okay, we can learn from these terrestrial planets because we have them right here in front of us. And
Right.
so that's incredible. That's just going to be, and James Webb, of course, will just
Right.
create a cornucopia of new planets. They're already coming every day. We used to have in my lab, we have a Friday afternoon lab meeting where we sit around and talk and drink beer or whatever the hell.
Right.
And it we used to have somebody who would we used to have somebody every week report on the number of new exoplanets. And
Right.
and then there got to be so many that we, oh yeah, another 50. It's just like, oh, we sort of did it every month or something like that. And there's hundreds and hundreds. It's incredible. So
NASA has a couple. What are the TESS is one of the satellite missions that we have, Kepler.
Yep.
And of course, James Webb is going to be.
Yeah, it's just going to be knock it out of the ballpark.
Amazing. Yeah. It's such a cool universe out there, but to me, it kind of blows me away. I've heard theories that there was a, universe is formed. There's galaxies, there's stars. They're born, they die, they explode, and then the material left over from that is what created our solar system. So we might be the children or the grandchildren of other stars, which is amazing. I mean, that is very profound to think about. I don't know if it's true or not. I'm just a fighter pilot, but it's a cool potential.
Yeah, absolutely. I don't know either scientifically, but I mean, it would be humbling. I think everybody could use a good dose of the fact that we're someone else's burnout ash.
Burned out supernova star.
Yeah.
So,
exactly.
So at the moon, but the moon helps us understand these things because you look at the composition, you look at the age, and we can kind of understand how the solar system was made and where it's going. That's great for the scientist at Brown, but there's also practical things right on the moon that could potentially be of economic value or help explorers. Is that right?
Yeah, I think so. I think just to step back though, one of the most important things for us here on this planet is to understand how our planet formed and evolved.
Yeah.
There's two factors that keep us from understanding that. The first one is what you observe from orbit, which is incredible weather and, erosion and things like that. And the second one, which is harder to recognize from orbit, from a visible point of view, is plate tectonics. So, in the time of COVID, the United States and Europe have moved apart faster than your fingernails are growing. Okay, I always like to use that one because people, oh my, okay, it's who cares?
Wow.
Who cares? But you multiply that by 100 million years, and you're moving the planet, the continent.
There's no more in North America. Yeah.
Yeah.
Well, that's another reason we talked about this last time. That's why you don't see craters on planets with plate tectonics, because it just erases them, right?
It does pretty much between that and the erosion, and we have them for sure, but they're really obscured, et cetera. So
they're young. Yeah.
Yeah. So the ocean basins, the ocean floors are less than 200 million years old, from 0 to 200 million, and that's 80%. That's less than 5 to 10% or so of the total age of the Earth. So the first 2/3 of Earth history is virtually almost all gone. We have some, but so if we want to know where we're going, we need to know where we've been, and we don't. And so where does the moon come in? A witness plate for what was going on in that early period. And even more fundamental was when we got there, people started thinking about this more. How did the moon form? Well, it appears to have formed from a huge Mars size, 1/2 the diameter of the Earth, impact into early Earth. And the eject from that went into orbit around the Earth and formed the moon. Wow. I always like to say, if you want to understand someone psychologically or just personally, you kind of would like to know what their childhood was like. Did they have any traumatic experiences that shaped their personality? Well, the Earth sure did. Okay, big time.
That would have sucked to have been around when that happened.
Yeah, you'd be breathing rock basically and vapor. Yeah, pretty much. Yeah.
Right.
Yeah.
So that's how the moon was formed. We think was a massive impact.
And
was the asteroid belt a planet at some point?
It
broke apart.
That's always been a question, and I think the consensus now is that it never really formed a large planet. uh, because the instabilities between Jupiter and the asteroid belt kept it from accreting, basically. So there's all
Right.
kinds of resonances back and forth. And some of these are what oftentimes in past history as ejected material out of the asteroid belt to come see us. You know what I mean?
Right.
Yeah.
Right.
So
So, and the other thing you mentioned, where we started and where we're going, climate change is obviously a big issue these days. And really, Venus and Mars are opposite extremes of climate change, but we could probably learn something from those two planets because there's definitely been some climate changing on both of them, right?
absolutely, that's one of the things we're discussing. In fact, I'm giving a paper at the American Geophysical Union meeting at the end of this week, which
Oh, cool.
is it's basically about whether Venus's current atmosphere was acquired in its visible history of the last 500 million or so years, or in fact is a fossil atmosphere inherited from earlier on. Many people think that Venus started out like the Earth because it has very many similarities to the Earth.
Right.
And then something happened to it that caused it to go into this, super greenhouse effect and heat up the atmosphere so that, like it's hot enough to melt lead on the surface, and the atmospheric pressure is like being a kilometer or two down in the ocean. I mean, it's really
crazy. Yeah.
It's 93 bars. Okay.
Right.
And so how did that happen? When did it happen? A lot of people think the Venus may have been Earth-like up until the last 20% of its history. We're looking at data from we've done global geological map of the whole region, and we're estimating the amount of lava coming out and the amount of gas that comes out from that. And we think that it probably was inherited from this prior to that time, earlier on in the history, and maybe was even original. So that's a big watershed. Is it recently like the Earth, or was it never like the Earth? And then probably the answer is somewhere in between. I always hate that. Oh, it's somewhere in between. No. You really need to understand that.
Right.
But
It's nuanced. That's interesting. I never thought about that.
and
Well,
then Mars, the same way. I mean, Mars is the other extreme, which is extremely cold, a very low density atmosphere, about a 600th, the thousandth, sorry, the density of the Earth today, and so how did that happen? We see evidence for water earlier. We can talk about this maybe another time, but we see a lot of evidence for water early on from flowing rivers and lakes, things like that, but the water's no longer there. So where did it go? What happened? Was it warm and wet? And did it turn cold, and why? So it's all related to climate change, long-term climate change. Yeah.
Yeah, absolutely. And, those are big questions. Remind me again, does Venus have a magnetic field and plate tectonics?
It has no plate tectonics at the present time. It's what we call a one-plate planet. Okay, it's not losing heat by convection of the surface. Okay, and it does not have a magnetic field at the present time. And so the question, the Moon had a magnetic field in the earlier part of its history. So that's another mystery. That's a really big question about how these magnetic fields form and evolve, and that's a big clue as to what's going on in the interior.
Can you see that on the Moon? Can you see rocks aligned in a certain way? Doesn't
No,
the magnetic field show that? Yeah.
So to do that, you would have to have plate tectonics, which created the crust, and then as the magnetic field is changing to do those stripes. There are none of those on the Moon, and plus, even if there were early on, they would have been obliterated by the impacts. But on Mars, there are some linear features that we discovered. When in one of the earlier Mars missions, in the last part of this millennium here, Mars Global Surveyor, when it went into orbit, it went in by aerobraking, which means that it dipped down into the atmosphere, as you well know, closer to the surface in order to circularize its orbit at a higher elevation. And when it did go down, it made some measurements and discovered some linear magnetic lines. And we still don't understand the origin of those. They must be in the crust somewhere. It does not look like there's plate tectonics. But one of the things we did, Terry, you'll love this as a pilot. We proposed a mission in NASA several years ago in which we would take a Piper Cub scale airplane, fly it to Mars, pop it out of the orbiter. It comes down in a parachute and then pulls out at about a kilometer, pulls out and flies for 1,000 kilometers with high resolution magnetometers so we could measure the details of that. It didn't get,
Oh
it
yeah.
got right up to the, it got right up to a choice between one or another. And
Oh man.
yeah, yeah, but it was great because it was at Langley Research Center, which is of course the Aeronautics Research Center. It was great,
Right.
a great mission. I hope it'll happen sometime.
Flying on Mars is fascinating. Well, let's talk about Mars. We're not going to have time to get into Mars today. It's been an hour already, and we're still at the moon. Like I said, this is going to be a multi-part series, if that's okay with you, because there's
Before we
so
go
much
to
to talk
Mars,
about. Yeah,
before we go to Mars, I could answer your question about resources on the moon. Is that
yeah. I still want to talk about that. Let's talk about the moon. Yeah.
okay? So yeah, so people have talked about resources on the moon, and why are we interested in resources on the moon? Well, of course, there's the dwindling resources on the Earth, but what do we know about the moon and resources? We know it's got a lot of titanium, okay, because Neil Armstrong and Buzz Aldrin, when they picked up the rocks at Apollo 11, they were extremely high titanium. They're almost ore grade titanium for sure. But you
Wow.
know, so do we go to the moon to get that? Is that economically feasible? That's out of my area of expertise. But the real one is that people want to think about is water. Okay, so we know the moon does not have an atmosphere per se. You know, it is you know, an atmosphere like the Earth's. It hasn't had, because the low gravity, all those molecules moving around, they just leave. Okay, eventually. And yet at the same time, when we look at Mercury right next to the sun, we see evidence for large deposits of water ice in
Right.
craters that are permanently shadowed. They're at the poles of the of Mercury,
Right.
and so water molecules coming out of the interior, like lava flows and gas,
Right.
maybe comets coming in and splot, and then where's the water go?
Right.
It finds its way to these coal traps and stays there. And so you know, if Mercury has them, doesn't the moon? Maybe. And there is some evidence certainly for water, but we don't know whether it's in water molecules, OH, you know, what type, and we don't know how much. So a lot of people think, oh, this will be great. We can make rocket fuel. We can drink the water. We can flush the toilets, you know, and, you know, we're always going, oh, before you flush the toilet, look, we need to look at that water. You know what I mean? It's like, this is really a resources, but
Yeah, we recycle it on the space station.
yeah.
You know, at tens of thousands of dollars a kilogram. This is I got a bottle of Coke here. You know, a liter of Coke or water would cost tens of thousands of dollars into orbit. To get it to the moon is probably hundreds of thousands of dollars.
Exactly.
And then to bring it back to Earth is probably like $1 million a kilogram. It's at current day cost. It's huge. That you would need to have some valuable titanium to make it worth bringing back to Earth, I think.
Yeah, and then of course what you really want to do is to be able to have a way station on the way to Mars, so that you don't have to take all that stuff up, and you can, you know, you can. This is also Elon Musk's plan for Mars, that that you know that there are demonstrable ice deposits on Mars. I mean, absolutely, we've been working with SpaceX to, you know, help them understand where these things are. Because yeah, they're definitely huge water resources on Mars, even in the equatorial regions. And it's ice that's left over from climate change on Mars in the equatorial regions. And
really, there's what? Where is? You can see it in the pole. I used to have a 5-inch refractor. You can see the polar ice caps. There's water there, but you can actually get it near the equator.
Yeah, and the reason for that is that Mars, unlike the Earth, does not have a huge body in orbit around it that stabilizes it against obliquity, against change in the rotational axis. Okay, so the Earth's moon is huge, and it tends to, like, okay, dampen the wobble from the axis. And on the other hand, Mars has a couple of space potatoes, you know, space butts, Phobos and Deimos. They don't do much. And so it's a, what was it? Some airline used to say, you're free to roam. And
Mars, Southwest.
Yeah,
it can, you're free to roam about the country.
Yeah, well, this is free to roam.
So Mars really changes.
Oh yeah, in fact, it changes a lot. When that happens, it points the pole towards the sun. Ice is mobilized up into the atmosphere, and it gets deposited coal traps, which are now at lower latitudes. Okay, and then once it goes back, okay, the ice sublimes away and goes back, but not all of it. And so, you know, you get debris on top. And so we have radar data from orbit. We've written a couple of papers on this. Radar data from orbit, it penetrates through the debris cover into these lobate features we see and shows that they're pure ice. and these are at 30 degrees north latitudes, and there's there's kilometers
Wow.
there. So yeah, so that's what happens. You can transport it through obliquity changes, climate changes, and then actually have the obliquity return towards a lower value, but leave some ice there for sure. Large quantities oftentimes.
So, and the moon also has a set, like Mercury has it, Mars has it, but the moon has ice in permanently shaded regions. Although, when I think about that, I mean, if you're talking about 40 Kelvin, so hundreds of degrees below zero, right?
Mhm.
And it's not like there's a ice skating pond there. It's buried under some amount of lunar dirt, and lunar dirt is called regolith, right? And that's not nice. It's not farming soil, right? It's pretty nasty stuff, I think.
Well, frankly, I've tried to avoid NASA using it for farming soil personally, but because we no, it's they've done some experiments on it actually in Apollo, but
Huh.
yeah, I think it does not have all the kind of nutrients because water
Right.
is what breaks things down into these and also life, organic molecules. I mean,
Right.
and so you're not going to get the same kind of soil you get on the Earth hardly at all.
But my point is, it's also kind of like crushed glass, right? A lot of the moon is silica, and so the
Well,
dust is hard to work with, I guess is what I'm saying. So if you have 40 degree Kelvin solid ice buried under meters of really nasty rock, that's going to be hard to get to
it is
potentially on
an
the moon.
engineering
Yeah.
challenge. We actually face this in Antarctica when we do our field work in Antarctica because the soil is ice cemented. Okay.
Right.
And so, you go, oh yeah, we'll just no, it's like concrete. Okay. And it's like incredible. I mean, you can send a shock up your spine by taking a pick and hitting through the soil to the layer that's ice cemented, and it just you ring for a week.
Right.
I think, and you're right about this too. The other thing about the lunar soil is that it's not chemically weathered so much as it is physically weathered. So that means that the impacts are breaking it down, melting tiny bits of it, and that creates a lot of glass,
Yeah.
and that's
Yeah.
really very dangerous to
Yeah.
breathing, and also to suit joints. Oh my gosh, I
Right.
mean, this
But
is a
even
big.
robots. So it's going to be hard to get. There is water there, but it's going to be hard to get it, I think. And
Well, yes, but we have not yet demonstrated, like you say, the amount and location of the water. Okay, there's
right.
evidence that there's some there in form or another, and I'm optimistic we'll find water. But there's a mission
Right.
going to the moon in a couple of years here, which called Viper, which will have a drill and have some experiments to try to detect that. And the Chinese will be sending a ground penetrating radar to the polar regions to assess this as well. So I think it's a big TBD. It's
Right.
one of the reasons we think there's so much ice at Mercury is not that, oh yeah, it was just going to be there, is that there was a recent impact about a few 100 million years ago that was a comet and dumped a hell of a lot of water into the polar region.
Oh, yeah.
So it's subject to scientific validation, I would say at the present time. And we have the missions that are going to do that, but I wouldn't. Let's put it this way. I wouldn't buy any lunar water stock for another couple of years, or maybe you should, and then take a chance. I don't know, but I'm
Buy low.
Yeah, buy low.
Yeah. Buy low, sell high. That's what they taught me at business school.
Yeah.
So there's water, there's titanium. I've heard helium-3 is another resource. Can you talk about that, or are there any other potential
Jack
resources?
Schmidt, you should get Jack Schmidt. By the way, it's the anniversary today of the Apollo 17 EVA3. 40.
Oh, really?
49 years ago today. Let's see, tomorrow Jack will be lifting off 49 years ago today. Jack and
I
Gene.
will send him a text after we're done. I'll send him a text. I didn't know that. It was December of 72. I knew that. So
Yeah. So anyway,
this might have been the day. This might have been the day that Nixon announced the shuttle. Remember, he called the Apollo 17 astronauts and said, "Hey, we're gonna have a space shuttle."
Yeah, my mind
Maybe.
was up. Yeah, I don't know. I don't remember, honestly. Yeah.
Yeah.
But the bottom line is that we sorry, you mentioned Nixon and it brought back a flood of bad memories there for a second. So what was the question again?
Helium-3, like there's helium-3 is a resource. Are there any other resources on the moon?
Sorry, I was momentary
But back to Watergate.
taser attack. Yes. So yeah, the Jack is big on that, and you
Yeah,
can mine it. I don't think we fully understand how to process it yet, and I'm not sure
right,
how much we can get from the moon that would last us for how long. Okay, so that's the
right,
key. Those are the keys. What's the grade? What's the transport mechanism?
right.
What's the refining mechanism, and how does that work? I don't, he's written books on that. He knows
He's
that.
expert. Yeah.
Yeah, I don't think the community at large thinks, again, this is the way to go for this. But you need to explore. You need to have creativity here.
Right. You
So
try different things, but that
yeah,
could be a fuel for nuclear fusion reactors potentially, which would make clean, emission-free electricity, which would be pretty great. But if it was easy, it would have been done already. So
and also that if how much is there on the moon, and how do we get it, and how do
I
we?
don't know. Yeah.
Yeah, I think I know Jack came to Brown a couple of years ago and gave that as part of his pitch, and people are going, a lot of the students are really kind of sensitive. Wait a minute, you're going to strip mine Mare Tranquillitatis and just to get a 100-year supply for the year? What?
Yeah.
It's those are the kind of things. There are indeed impacts, environmental impacts on other planetary bodies. Maybe we don't, in the fond tradition of the human species, maybe you don't give a damn. You know what I mean? We just,
Yeah.
it's all there for us, folks.
That's an interesting question. Planetary protection. I remember going to NASA headquarters and there was an office of planetary protection, which is pretty cool. On the one of the jobs is protect Earth from asteroids, but another one is to make sure that, we don't contaminate Mars with life. And I think when you make these probes, you're pretty careful about irradiating them and trying to minimize the amount of microbes and stuff we send.
Yeah. Yeah, we do. There's a huge effort that goes into essentially sterilizing them in the best possible way. I have to tell you a quick story about the planetary protection officer. I was on a podium with her, on a stage with her one time, and we were backstage talking before we went on. And I said, I've always wanted to ask you, do you actually have a badge for planetary protection officer? And she said, yeah. She's look at it. So I said, oh, I got to get a picture of this, and put my arm around her. We're talking, holding the badge up. She says, I'm sorry, I'm kind of like, I got something. I don't know what it is. So a day later, I come down with whatever this crud was,
God.
pre-COVID. But I've always been proud that I was infected by the planetary protection officer,
whose job is to not send microbes to other planets. That is funny.
Yeah, it was hysterical. I mean, but she has awesome. A badge. It's great. I mean, I'd love that.
I was walking through and I was like, I saw this office with this little, sheet of paper printed out on a laser printer. That's a good job title. But I remember a story about how Apollo 12 landed next to one of our robots and they brought it back. Mm-hmm. And didn't they find microbes that had survived from Earth? We're out in space, and yeah.
That was a really important story, because one of the things we wanted to do on the second mission, Apollo 12, was to pinpoint land so that we could say, hey, we can go anywhere on the moon we want. Okay. Because Neil had, for good reason, landed long, a few kilometers long, because of the rocks and stuff like that. And so Bob Gilruth, the head of the NASA Center at the time, wonderful man, he said, we got to get a target for the engineers. And what about you guys want to land over here, you scientists? Isn't there something over there we could? It was a Surveyor 3 spacecraft that had already landed there a couple of years before. So that's exactly what we did, and they landed right next to the damn thing. It was just incredible. And so so that's a prelude to the fact that they were able to go. Alan Bean and Pete Conrad were able to go over to this and actually cut things off and bring them back to see how they'd survived, how the glass had survived micrometeorite. And in that, I think it was the cabling, Earth organisms were detected once it got back. I don't think it's ever been unequivocally demonstrated that they actually went to the moon and came back from the moon and survived, or actually were contamination when it got back. I don't know the answer to that, and I'll try to check.
It's a good urban legend, though.
Yeah. I mean, it's entirely possible. I mean, possible that, the cabling in there, it's pretty protected.
Right.
So yeah, and life.
That is a cool.
Life being what it is, I mean.
It's pretty resilient. It's pretty amazing.
Yeah.
Well, Jim, I tell you what, it's been an hour, over an hour. Why don't we call it at the moon, and next time we'll move to Mars, if that's okay with you.
Hey, it's my favorite place. I spend most of my day there.
Well, let's do that. This is so much fun. I could talk the space station's cool, but it's this robotic stuff is what really gets me excited, and planets and other stars and stuff. So thank you for your time today.
Oh,
We're going
my
to have a
pleasure.
lot more to talk about. We've got Mars. We'll keep on moving out to the outer planets. And so probably at least a couple more episodes. We'll see how it goes. But have a good Christmas and holiday season. And thank you for coming on today. And if, by the way, Down to Earth with Terry Virts, if you love it, please don't forget to subscribe and give us a rating. So thanks for coming on, Jim.
Okay, thanks very much, Terry. Always a pleasure.
All right, bye-bye.